Alright, today I want to show you a number system that I designed a while back, a few years ago, that violates the basic principle. There's always crap on whatever surface I'm going to use. That a number base has to have as many symbols as the size of the base. So if you want, basically if you want a number base that has a bunch of factors, which makes it really nice to use, you have to have a whole bunch of symbols, which makes it really shit to use. So you end up with this terrible compromise. So what we've landed on is basically recognizing that base 12 is a really nice place to be, but because of stupid Roman traditions, we use base 10 instead. Anyway, so the first part of this, I'm just going to show you a basic numeral system, which is pretty nice, pretty intuitive. I think you're gonna have no problem with this, right? So 1, I don't see how that shows up. 1, just like basically a dot. 2, 3. So the idea here is this is 1 dot, this is 2 dots connected in cursive, this is 3 dots connected in cursive, and this is actually literally where 1, 2, and 3 came from. 4, it's like a cursive X. This time it has a loop on the bottom, but it's a cursive X, and this is actually how we got our 4 also. And then so this is actually traditionally related to where our numerals came from anyway. 5, I'm going to switch kind of into Mayan now. 5. And then, for the most part, it's now going to operate like Mayan. So 6, 7, 8, 9, 10. But it's going to become convenient to introduce some conventions here. So 6, we're going to actually at some point need a distinct symbol for that. So here, just kind of like a variation on the line plus the 5. So it kind of looks like Lamed, yeah, like a Hebrew L. The 10, you could, if you wanted, you could represent it as an X. If we say we get to 15, is it still on the screen? Come on, camera, focus. So 15, you might want to do something like this, basically like an N, just to keep it cursive. But these things aren't necessarily. The 6 is going to be really nice, but the other ones might just be like cursive conventions. Okay, so we have now a way that we can count all the way up to 10 using really just 5 symbols. This is even if we're considering this a single symbol, it's really a compound of a 1 and a 5. Right, there's your 1, there's your 5, and there's just a cursive stroke between them. Okay. What are you rabbits doing? Holy. Okay, so what we want to do is we want to find a large, useful number base, especially one that might have cultural relevance. So how about base 60? What if we sort of used this, maybe along with some Mayan, using base 20 and get up to base 60, right? So 60 is 3 20s, okay? Now, the way that this is going basically I'm putting, I'm like prefixing the smaller components onto the 5s. So if I also prefixed the number of the next unit up to that, it could get confusing. So if I postfix that, right? So put, say, so we're counting up to 20s. Say I want to say I have 2 20s and 3 or something like that. It would make sense to do this, right? So this means I have 2 20s and 3, so this would be 43. Okay. And then 60 would basically just be, well, let's see. Let's add another one. We need a 0. Just like a flat line would be nice, but this is much more distinctive. Okay. So 60 would be like 3 20s, like that. Okay? Now, the problem now is if we just stack 60s, we never get, well, the nice thing about using 60 is we can divide by 1. You can always divide by 1, kind of. Now, as long as you're using integers, you can divide by 1. So you have a factor of 1, you have a factor of 2, you have a factor of 3, you have a factor of 4, you have a factor of 5, and you have a factor of 6. 7 is missing. 8 is not too bad because you just end up with a half. 9 is not horrendous, but it's not really going to work directly. 10 works. 11 doesn't work. 12 works. And nothing larger than 12 until we get to, well, let's see, 15, and then 20, and then 30. Right. So there's some gaps. It does take all of the numbers that you probably know how to represent on your hand nicely. 1, 2, 3, 4, 5. And that's probably where you end because you'll probably represent 5 this way because nobody taught you how to count on your fingers in a way that makes any goddamn sense. So you probably end up here, but you miss 7, 8, and 9. So on the way up to 10, you missed 3 of the numbers. Okay. If we stack 60s, you can get 8 and 9. So you're still missing 7. And you're missing 11. And you're missing 13. If you had a number system that caught 7, you'll eventually catch 12 as well. Or, I mean, 14 as well. And we already have 15. 16 is taken care of because there's 4s and 2s going on. 17 is going to be the first prime number that I'm going to ignore. Right, so I'm going to show you, using just this, how to get a number system that will incorporate every number up to 13, all the prime numbers up to 13, and really all of the numbers up to 16 as reasonable factors. They might not be direct, but they'll show up. Okay, so what happens if we have, say we had 2 60s multiplied together? Now I'm going to use standard Arabic numerals, right? So 60 by 60 is 3,600. So what we need to do is we need to get 7, 11, and 13 in here. Okay. Well, what if, so this is 6 10s. What if we just straight up did 7 by 11 by 13? And then this is going to be too small for sure because 13 is much smaller than this. So, okay, 7 by 11 is bigger than this. This is like, what, 5 12s? So what if we did 4 13s? What does that give us? Well, that gives us 4,004, which is, these are kind of comparable. 3,600 and 4,004, they're not super far off from each other. Here, we get a 77, and here, we get a 52. Okay, now, this number turns out to actually show up all over the goddamn place in modern culture, right? How many weeks are in a year? 52. How many days are in a week? 7. So this is already almost exactly representing 11 years. 7 weeks of 752s is 364. So it's not exact, but it's really, really interestingly close. It's tantalizingly close. Like, this is very similar to something that we use. So that's interesting. You know, a deck of cards, right? You have four suits of 13 cards for 52 cards. 52 does show up. But it's awkward in a base 10 system because of the 13, really. The 4 isn't too much of a problem for base 10. It's slightly annoying, but it's not too bad. The 13 is a real pain in the ass for base 10. And it's, you know, base 60 doesn't resolve that in any way. So, what if, now this is where our 6 is going to come in handy. Representing, okay, so this one is going to be, let's see, so we got some tricks going on here. Okay, so what's happening if we wanted to represent, say, 59? So we kind of backtrack so you can show what's going on here. So this is 60, but I wouldn't really represent it that way. What I would do is I would turn that into, whoops, whatever, kind of a little comedy-ly. I do it like that. So 160, one full 60, right? 59, one less than this. So this kind of looks like 100, right? This is, or 10 or something like that, like 1 0, right? Okay, so 59 is going to be, it's 2 20s, not 3. It's not 3 full 20s, right? So it's 2 20s, and then 19, right? So we've got, there's our 15, and then 4 in front of it. So there, we're not actually ever having to represent 20, a full 20. Because when we have a full 20, we mark it over here, okay? So, over here, we don't ever have to represent a full 11. One less than 11 is 10. We can already represent 10. So, 76 now just becomes 6 groups, or 6 groups of 11, so that's 66, plus 10. All right, so that is 76. This is 59, right? So I sort of changed our number system, like the way that we're looking at the numbers, but I got it to represent a completely different, right? All I had to do was add the 6, and now I can handle this very nicely. Similarly over here with the 13, well, the way that we got 10 was we doubled the 5. So here, what we can do to get 13 is we can double the 6, and that means that we can represent 12, and we're never going to have to represent a 13, right? So, 51 is going to be 3 groups of 13 plus 12, right? So 3 groups of 13 plus 12. Okay, so now here I introduced something. So what we're going to do, we're going to have 2 60s, a 77, and a 52, and that's going to be our order, right? 60 by 60 by 77 by 52, and that's going to be our unit. That's going to be our, basically that's our number base. And what we're going to do, this is going to be the thing that we actually repeat over and over and over. But because 77 by 52 is pretty similar to 60 by 60, it's going to sort of act in the way that it scales, like we're using just base 60. But we're being a little more clever and we're able to get more factors in here. So we need to come up with some symbols that will break this up for us. Right, so say I've got, here I've got, I don't know, like 13 or something, right? So there's 13. Okay, move on to the next 60. And say here I've got, I don't know, 25, right? So 25. So there's 160, there's 160. Now we're into the 77s, so let's say over here, what do we have? I don't know, 58, or something like that, right? So 58 is going to be 5 11s. Okay, so 5 11s plus 3. Now, you might be thinking, well, that looks like a 15. But, recall, in the 77 group, we can't get a 15 because we're only, over here we're using groups of 20. So you can get a 15. 15 is less than 20. But over here, we're using groups of 11. 15 is bigger than that. Or, what am I doing? 8. What the hell am I talking about? 8. Why did I multiply these? Okay. Never mind, my point doesn't work here. Okay, so 8. I had a convention for this. I don't remember what it is. Oh shit. Yeah. Okay. Anyway, so it can look like an 8. So I guess I gotta be careful with that. Maybe it was with using the 0. Maybe something like that. I don't know. There's ways you can make that work so it doesn't look like an 8. Coming to the end of the video, I am going full retard. Okay. But now we need, so we're marking the 60s with this little suffix, this little D dude right here. So, let's just be lazy and do one up here. Okay, so that's marking, this is your 77 group. Alright, now we've got 52, so say we've got just exactly 13. That's going to be that. And then we'll close it off. There you go. So now, if you wanted to go further, and then the next one, let's say it's, I don't know. Nope, we can't do that because that's 80. Mwah, mwah, mwah. So you can't just put the symbols together randomly. So say it's, I don't know, 14. Um, 47. Straight up, just 6. 3. I'm lazy. Right? So now this whole block becomes the thing that you repeat. And our number base is whatever those two multiplied together is, which is a big number. I used to know it. It's 4 0.0004 by 3600 is, well, that's a big number. So these give us a base of 14,414,400. So under conventional wisdom, in order to use a number base this large, I'd have to have that many symbols. But we don't have anywhere near that many symbols. What do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, look at that. I have the same number of symbols as decimal does, but I can use this number base, which gives me the ability to have factors 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, skip 17, go to 18, skip 19, go to 20, right? 21, 22 will work. Yeah, so we can now, using this, we can have a number, you know, whatever. You can represent stuff, any number with this system, and you can now handle it in a way where you can divide by not anything, but far more things. Yeah, okay, so also let's see. Say we've got, you need to represent decimals, right? Okay, let's just say this is your decimal point, basically, that little dash. So now it's still the same number of symbols as your base 10 uses, because you use a point. Here we're using a dash. Right. You can do real math with this. Well, I don't understand why we're being stupid. I also don't understand why anybody would say that your number base has to have the same number of symbols as your base anyway, because Babylonian base 60 doesn't operate that way. Babylonian base 60 is base 10 inside the base 60, right? And I'm using a similar thing. I'm using a base 20 inside the 60. I'm using a base 11 inside the 77, and I'm using a base 13 inside the 52. It's the same trick. I just used it in a way that everything ends up coupling to work out really, really nicely, so that also, there's some nice things with this. So if we take this base and say we raise it to a power like 3 or 12 or something, right? I like 12. Let's go to 12. Raise it to the 12th power. It's now sort of on par with Avogadro's number. So what you could do is you could just replace the mole, the Avogadro's number in the mole, with something like that, and now it is a perfect cube, and it is a perfect square. So you can now you can actually physically, theoretically, make a block of silicon or something that has exactly one mole, one new mole, this to the 12th power or something, of silicon atoms, but it's also a perfect cube. Or you could make a wafer, a silicon wafer, a square silicon wafer that is exactly square, but also has exactly one new mole of silicon atoms. Things like this. You can do much nicer things down the line than you can now, and it's not that difficult. Like, I fucked it up, but I don't use this on a daily basis. I haven't actually looked at this in months. I was like, I don't know what I'm doing. There's a few places, as you've noted, that I just went stupid, like referring to an 8 as a 15 because so I was multiplying, I think. Yeah. Anyway, there's ways to do this that are really, really elegant, and this is at least an introduction to the realm of possibilities here. If you understand what I'm showing you, good. I feel like if you got this far into the video, you understand what I'm showing you, that there's something here. Anyway.